of Chapter 4, Physical and Chemical Change, and this should cover pages 4 through 8 of your outlines. So in this section we're going to be talking about primarily chemical reactions and how we can represent those as an equation. So remember, a chemical reaction simply allows a chemical change to occur. For example, if we have a molecule of water that can break down to H2 molecules and O2 molecules. Up here on top you can see that we have the molecular structures represented. We have 2 molecules of water, and on this side you can see we have again 2 of the H2 molecules and 1 O2 molecule. This down here is our chemical reaction equation. We see 2 molecules of H2O will become 2 molecules of H2 and 1 molecule of O2. So going back to a chemical change, remember that is when we are starting with one set of substances and ending with a different set. Our reactants are those chemicals which we start with, and they are written on the left side of the chemical equation, and products are those chemicals that we end with, written on the right side. So just remember that we are reading things from left to right. Okay, the stuff on the right is the stuff that's being produced, and the stuff on the left is the chemicals and molecules that are reacting. Okay, reactants on the left become products on the right. Again, if we take a look at that chemical reaction equation, it will tell us what molecules are reacting and which molecules are being produced. Okay, we're not going to always be drawing the chemical structures or have models to build. Okay, so it's important that we understand what these equations actually mean. Now the equation you saw before, you noticed on the right side it said unbalanced. Okay, all equations must be balanced. And that's because conservation of mass tells us matter is not created and matter is not destroyed. So whichever atoms we're starting with have to be the same atoms we end with. The only difference is we've broken the bonds and rearranged the atoms. So if we look at the reactants side, here if we have a balanced equation, we can count up how many H's do we have on the left. And here we can see we have 4. So that means I have to have 4 H's on the right, which I do. If we count up the oxygens, you'll see we have 2 on the left, and that means I have to end up with 2 on the right. So everything is balanced. Rules for balancing a reaction equation. We do not change the subscript numbers. Remember, those are the numbers that are in the chemical formula that follow the element symbol and are slightly to the bottom. Okay, we may only change the coefficient numbers. Well, what does a balanced chemical equation mean anyway? Why do we care about them? Well, it's because chemical equations are like recipes. An unbalanced equation will tell us what we're using, what the ingredients are, those reactants, and they'll also tell us what the result is, the products. But it doesn't tell us what the proportions are. An unbalanced equation doesn't tell us how much. Okay, once we have balanced the equations, then we know exactly how much of the reactants are needed, and it tells us how much of the products are made. Okay, and those coefficient numbers refer to moles. Okay, the units for a balanced chemical reaction equation are moles. Okay, for example, let's look at a common reaction that those of you who took AP Bio should definitely be familiar with, and if you didn't, that's okay, it still applies. Okay, we know that there are 6 moles of water that react with 6 moles of carbon dioxide, and that process will yield 1 mole of glucose and 6 moles of oxygen gas. Okay, so our reactants here are water and carbon dioxide. Our products are glucose and oxygen, and these numbers out in front, the coefficients, tell us how many moles we are using or producing of each of these different compounds. When there is no number out in front of a chemical formula, that simply means that only one is being used. Okay, just like if there's no subscript, that means it's only one atom. For whatever reason, we don't write a lot of ones in here. So hopefully that's clear. There's no number, just assume that it's a 1. The reason why it's important for us to know that these chemical reactions are actually in units of moles is because the moles can be used to calculate grams of the reactants needed or the grams of product that are made. And keep in mind, grams are what we are measuring when we are in lab. So we're using formula masses then as conversion factors. Okay, so now you understand why we have to be able to convert these grams to moles. It's because all of our chemical reaction equations are written in terms of moles. Okay, so that's why we have to be able to use that conversion. Hopefully now it's starting to kind of make sense. Again, conservation of mass tells us that the total mass is conserved. In other words, the grams that I'm starting with should be equal to the grams that I am ending with, which should make sense if we're starting with the same numbers and types of molecules on the left, of atoms on the left, and ending with the same types of atoms on the right. It should make sense that the mass doesn't change. Okay, it's not magic, it's just science. All right, so if we convert our 6 moles of water to grams using the formula mass of water, right? Oxygen is 16, each hydrogen is 1, add them all up, we get 18 grams per mole. We've practiced doing this. Then we have 6 moles times 18 grams per mole. Moles will cancel and I get 108 grams. And it's that same process that we've used going through to get what the mass is of each of the reactants and then what the mass would be expected for each of our products. Now if you add 108 and 264, you'll see that that is equal to 180 plus 192. So it actually works. When we have chemical reactions, some of them will absorb energy, and that happens when the energy level is higher for our products, and so energy has to be given to move that energy level up. And some reactions will release energy, and that happens when our energy level is lower for the products versus what we start with the reactants. So that energy has to go somewhere and it's released. For instance, we have endothermic reactions. If we break up that word, endo means into or entering, and thermic means having to do with heat. So an endothermic reaction is where energy or heat is entering the reaction. It's absorbing energy. And in order to absorb energy, energy has to be added to the reaction. So here is, again, going back to the photosynthesis reaction. Photosynthesis requires sunlight. Plants have to have light to be able to take the water and combine it with the carbon dioxide. And that energy is added to the reaction. So it's a reactant, really. It's written on the left side. It's energy that has to be added. This reaction will not happen without this energy from the sunlight. So it is an endothermic reaction. Okay. Exothermic then is the opposite. That is a reaction that has heat exiting or moving out of it. So that energy is being released. Okay. The opposite reaction of photosynthesis is respiration. This is what we do. We take glucose, combine it with oxygen, and make water and carbon dioxide. Now, that is a reaction that releases energy, which is great for us because we use that energy. So respiration is exothermic. Notice that the energy that's being released is written as a product here. It's being produced, and this energy is then exiting the system. Okay, so I've used the word system. It's important that you understand what the word system and surroundings mean. Okay, energy flow has to be constant, just like, you know, conservation of mass says the amounts of mass has to be equal. the energy flow has to be constant. In other words, energy that's coming into the reaction has to come from somewhere, and energy that's being released has to go somewhere. So we're going to call things in terms of system and surroundings. And when we say system, we simply mean the chemical reaction itself that's going on. The surroundings would be everything else. So in terms of an endothermic reaction, that's where energy is being absorbed by reactants, which means energy is coming from the surroundings. Okay, so it's flowing from the surroundings into the system. Whereas exothermic, when we have energy released by the products, that's equal to energy given to the surroundings. So energy is flowing from the system to the surroundings. So again, here we have photosynthesis at the top. This is energy that is going in, respiration on the bottom, and that energy is going out. I apologize for this typo up here. So looking again at respiration, the energy is flowing here from the system to the surroundings. Okay. Activation energy is important to understand when we start talking about chemical reactions. Okay, reactions don't just magically occur spontaneously. It might seem like they're occurring all on their own, but the reality is every reaction requires a minimal amount of energy to be applied first. Okay, in order for those atoms to recombine and make new substances, we have to break those initial chemical bonds. So just like it takes energy to separate two magnets, it takes energy to separate two bonded atoms. Those energies will vary, but once we've got those atoms separated, then we can make new bonds. Okay, and activation energy simply is the term that's given to that energy which is needed to break the bonds in the reactants so the atoms can recombine to make the products. And here we've got a great little diagram that shows you. If reactants are at this energy level, okay, we can see that the products are, for this particular reaction, are going to be at a lower energy level, okay? And here, though, we see we have this peak in energy, and it's because the reactants need to have energy added to break all of those bonds and get those atoms out of molecular form and into single atom form so we can then make new bonds, okay? And this energy right here, the difference between the reactants and this peak amount of energy, that energy which is added is called the activation energy, okay? That is the energy that's added to break all of the bonds in your reactants. Now, once those bonds are broken and you have the single atoms, they recombine and can make new bonds, okay? And here we can see all of our new bonds have been formed, and this is our final energy level. Now, reactants will not always have a higher energy level than products. Sometimes your reactants will have a lower energy level than your products. Here we can see that reactants are moving to a lower energy level in product form, and so all of that energy is energy that is released. So is this an endothermic or exothermic reaction? If energy is released, it's exothermic, okay? So if it were switched and the reactants were down here and your products were up here, then we know that in order to go to the higher energy level, reactants had to absorb the energy, okay? And that would be an endothermic reaction. But either way, this little peak right here, the difference between your reactants energy level and this peak energy level is always the activation energy. And that's something that you definitely need to know and something that we're going to be coming back to often. Here is your Chapter 4 homework. Page 128, numbers 1 through 27, 36 through 39, 43 through 47, 50 through 54, 57, 58, and 71.